Well, hello, everybody. Welcome to another program as part of Astronomy Days. I'm your host, Chris. I work here at the North Carolina Museum of Natural Sciences, and it is good to be with you for another edition of these programs. We've been learning so much cool space stuff all week long, and I think this presentation right now is going to be just another gold star on what has been a fantastic 7 days of Astronomy Days programming. Make sure that you go back, check out the museum's YouTube channel and the Astronomy Days 2022 playlist, because there are a lot of amazing videos on there now of our past presentations from this week. You don't want to miss any of the great knowledge, insight, and just cool stuff that's available to you there. As we get seated and settled into today's presentation, into this Zoom, I'm curious, got a question for you. Have you ever seen a comet? A comet, so, streaking through the sky, ever seen a comet? And if so, do you know which one it was? Like, they have names. What comet have you seen if you've seen one? I'm going to check on your answers in just a moment. While we do that, I want to go through a quick Zoom tutorial for those joining us on Zoom to make sure that you can take advantage of the best viewing experience and the accessibility features that we have for you. Now, first off, everybody's audio and video should be turned off. If it's not, you can double check in the bottom left-hand corner. But then in the bottom middle of your screen, you'll see a button labeled Closed Captions. We do have live captions available for you to take advantage of. When you click that, you'll get a menu and then click Show Subtitles to bring those up. You can also click Subtitle Settings and make adjustments as needed in order to take full advantage of the captions and that feature. Now, in the program, we think the best way to view here on Zoom is to be watching in speaker view. That way, whoever's talking, their camera pops up. And then over on the View Options button, make sure that you have side-by-side mode checked. That way, you can see the full presentation screen and our guest speakers both on your screen at the same time, one not obscuring the other. So that's the best way to take advantage of the Zoom, we think. And of course, there's a little slider bar between the two. So during the show, if you want to make the speaker larger or the slideshow larger, grab it and drag it left or right. Of course, all of our Astronomy Days programs engage you as well. These are interactive. So as we go through the program, make sure that you're leaving your thoughts, comments, and questions in the chat here on Zoom. And if you're watching on YouTube, you can type into the YouTube chat as well. We have moderators who are in both places who will make sure that your questions get to me so that after the presentation, we can ask them. But of course, if you're going to be in the chat, we expect you to be nice to everyone else who is in the chat and be nice to our guest speakers. All right? Sounds good. And I think with that, we should get started. Now, I'm going to take a look over here at some of our comet answers. Let's see. Rachel did in 1986. Dan has seen Halley's, Hale-Bopp, West, others. Neowise. Wait, oh, Neowise. Is this the one that was most recent, Rachel?
Yeah, that was the one a couple years ago that was visible in North Carolina with binoculars.
Yeah, I think the last one that I was able to see was ISON, which was a few years ago. I think it was visible. Hopefully, I'm not confusing it with another one. But everybody, I should introduce Rachel. Dr. Rachel Smith is the head of the Astronomy and Astrophysics Research Lab here at the Museum of Natural Sciences, and she's a professor at Appalachian State University. Hey, Rachel.
Hey, Chris. Hey, everyone. So thanks for coming. I'm just going to quickly introduce my friend and colleague, Dr. Ryan Oglior, and I'm really excited to hear his talk on comets and early solar system materials. So thank you all for coming. It's been a really fun Astronomy Days. And so this is great. So let me quickly introduce Ryan, and then he will take the floor. So Dr. Oglior is an assistant professor of physics at Washington University in St. Louis in the Department of Physics. He specializes in microanalytic techniques, so looking at really tiny things in the lab to study extraterrestrial materials. So the little tiny stuff, we've heard a little bit about it this week, if you've been to some other talks, in meteorites and their sample return from asteroids. And he's going to tell us what we can learn from these micro analytical techniques of samples. And he also looks at techniques to look at grains from other stars, or like these pre-solar grains before our solar system. So he's an expert in all of these techniques. He got his bachelor's at Claremont McKenna College and his master's and PhD at Caltech in Pasadena, California. And he's a great guy. So thank you, Ryan, for taking the time to talk to us. And please take it away. Give you the floor now.
Awesome. Thank you, Rachel. Yeah, if you haven't seen a comet, I recommend it for the next one. They're truly spectacular. This is Comet McNaught I'm showing here. My favorite was Hale-Bopp, which was back in the late 90s. It was really unbelievable. So they're super cool celestial objects, if you can see them. Okay, so I'm going to talk about the solar system's formative years. And because this is Astronomy Days, we'll go ahead and talk about a very cool astronomical object to start with. This is the Orion Nebula. It's naked eye visible if you're lucky enough to live in a place with very dark skies. It's quite large. Its angular size maybe is close to the full moon. It's super important because it's the nearest large star forming area to us, to the Earth and the Sun. It's about 1,200 miles or something from us, from the Sun. And inside the Orion Nebula, there's several hundred stars in various stages of their early star formation. So this is one such star. It's a relatively small star, probably about the same size as the Sun. And you can see that dark material right in the middle. And what that is a forming solar system, a forming planetary system around this other star. So if we can study these systems in detail, we can learn about this general process of planetary formation in the galaxy, and also what might have happened in our own solar system. And this is a very exciting time for this branch of science because there's new astronomical observatories, and these are multi-telescope observatories that are allowing us to see these forming planetary systems in really unprecedented detail. And one that I'm super excited about is this Atacama Large Millimeter Array in Chile that can actually see little bands in this protoplanetary disk that are being carved out by forming planets. So we're actually witnessing this process of planet formation as it happens. So we also have data from the Hubble Space Telescope, and pretty soon we're going to have data from the James Webb Space Telescope, which we heard about earlier this week in Astronomy Days. So this will really help us understand the atmospheres and the compositions of these exoplanets that we now know are quite common in the galaxy. There's as many exoplanets as there are stars in the galaxy. So about 5 years ago, we found this system, TRAPPIST-1, which had 7 rocky kind of Earth-sized planets around a single star. So we really know now that these planetary systems, which maybe aren't too different from our own, exist in the galaxy. So this is a very exciting time for this field of understanding planetary systems elsewhere. And these are all kind of new discoveries, and that's going to be the focus of my talk today, is more recent advancements in knowledge in this field of study where we're thinking about forming planetary systems. So in my research, I seek to answer this question, which is, what are the sequences of events that produce these varied worlds that we're seeing in exoplanets, but also that we see in our own solar system? So we start off with this very primitive cloud of dust and gas, and we end up with these amazing varied worlds and moons and asteroids and comets and Pluto that we see in our own solar system and that we're seeing elsewhere in the galaxy. So what were those processes that led us from this cloud of dust and gas to the planets we see now? So in particular, I'm interested in how planetary systems like ours form, and the like ours is a very important part because part of this research is to understand this question. One of, I think, the most fundamental questions in science is, are we alone? Is there intelligent life elsewhere in the universe? And to understand that, to understand intelligent life as we know it, how that evolved, we're interested in how planetary systems like ours evolved, because we know that intelligent life evolved at least on one planet in our own solar system. So to answer this question, I really like this quote from Norbert Wiener, which is, the best material model of a cat is another or preferably the same cat. So if we want to know how planetary systems like ours form, the simplest and the most really illuminating thing to do is study our own planetary system. So if we want to study how cats form, we look at a cat, and the same thing is true with our solar system. So this is kind of the guiding philosophy of my lab and the other scientists that work with me here at Washington University in St. Louis. We're in the physics department. We have a floor up here with lots of really cool instruments that help us answer these questions. And a guiding quote for us is from Victor Hugo's Les Mis, which is, "Where the telescope ends, the microscope begins. Which of the two has the grander view?" And if you ask me this question, I'd say, well, the telescope has the grander view, but the microscope has really the more precise view, which tells us a lot of amazing things about the formation of the solar system. So another thing I really like about this field where we study actual solar system materials is that it's incredibly multidisciplinary. So we have to know astronomy, physics, earth science, chemistry, nuclear physics, all of these things, and no one person can be an expert in all of these things. And so it's very collaborative. I'm always talking to other people at the university, at other universities like Rachel Smith, to learn things that I don't know. So I like that interaction, and hopefully we'll get back to going to conferences, which is a very productive part of my career because I learn these new things that I don't know about. So if we look at a real rough timeline of the solar system formation, we start with a cloud of gas and dust, which is a fragment of an object called a molecular cloud that we can see astronomically. So about 4.5 billion years ago, that cloud likely collapsed. And because it was spinning ever so slightly, physics tells us that when it collapses and gets smaller, its kind of rotational momentum has to be conserved. So that caused that cloud to kind of squeeze down to a disk, a rotating disk, and eventually, through some very complicated processes, that dust and gas accreted together and formed the planets and moons and all the things that we see in the solar system today. So if you talk about the types of tools that will help us understand this process, going from these 5 different steps that I'm showing here, really, probably the most important process to understand the timing of these events is radioactive decay and measuring isotopes of different elements. And my friend Pierre Hanakour talked earlier this week about isotopes. So if you're there, you got a little primer, but if not, I'll give you that now. So what happens here is we have a parent nucleus and it has some number of protons and neutrons, and it decays to another element that has a different number of protons and neutrons. So during that process, it emits some form of energy. It could be gamma rays, it could be a helium nucleus like shown here. It's not really important for what I'm talking about today, but it undergoes this change, it emits energy, and it becomes something else. And the important thing about this process is that it's somewhat random, but if you took 1 million, 1 billion of these atoms, you could constrain the rate at which these atoms decay. For just one, I can't tell you when it's decay, but if we have 1 billion, 1 trillion of these things, I can tell you when half of them are going to decay. And that's the quantity that we call the half-life, which you may have heard before. So one tool that we have in geology, or this kind of cosmogeology that me and my collaborators engage in, we can use the decay of uranium isotopes, really heavy atom. So when this rock crystallizes, it crystallizes with a certain number of uranium atoms, and then say 1 half-life later, about half of those uranium atoms decay to lead atoms, and 2 half-lives decay, and more time goes on. We build up more and more of that daughter nucleus, that lead nucleus. And if we measure the ratio of that uranium to lead, that can serve as a clock. So we use that as that clock to determine when that rock first crystallized. So with this particular case of uranium, say we form some important object at the beginning of the solar system's history about 4.5 billion years ago. And we have 2 different isotopes of uranium that decay at different rates. And we can look at their decay products, which is lead. Its abbreviation is Pb. So we decay 238 uranium to 206 lead. We decay 235 uranium to 207 lead at different rates. 235 goes a little bit faster than 238. And we could look at the relative abundances of lead and uranium when we get that rock in our hands today, and that tells us when that rock crystallized. Okay, so this example is uranium lead, but we actually have a lot of these different isotope systems that we call them, that serve as clocks. And there are several, and they're really important because they're different elements, and different elements behave different in a geologic context. So some elements, say aluminum, may be useful for dating different kind of events than, say, manganese or iodine or some of these other radioactive nuclei. And they also decay at different rates. And so we can kind of explore different time scales. So if we're interested in billion-year time scales, we can look at uranium lead. If we're interested in million-year time scales, the most useful chronometer that we usually use is an aluminum, just like an aluminum can. Your aluminum can's made of 27 aluminum, but there's a radioactive isotope aluminum that has one less neutron, aluminum 26, that decays at about 750,000 years half-life. So we use that to date kind of shorter processes in the early solar system. So this will allow us to construct this solar system timeline, which may or may not be the same as a different solar system elsewhere in the galaxy. I think it might be similar, but if we precisely determine this timeline, that gives us insight into what other planetary systems do in this first few million years. So this is the process that I'm going to talk about today, is that first really 5 million years. And I talked about the techniques that allowed us to do that, which were measuring those radioactive isotopes and their decay products. But to employ those techniques effectively, we need the right samples, right? And here I'm going to explain to you how we have the right samples, because you might think, why do we have samples from this early time in the solar system? That doesn't really make sense. And how does that help us? So we're interested in how these planets formed. And as an analogy, we can think of a biologist that might be interested in how all these different types of animals formed. I'm interested in this. I don't study biology, but it's fascinating to me. So if I wanted to learn how all these different types of animals formed, their origins, I may want to look at something that predated these animals, right? And that could be something like a dinosaur. But unfortunately, I don't have access to a living dinosaur in the lab. So maybe there might be some species that escaped these pressures of evolution and have remained mostly the same for a long, long time. And it turns out there are a few of these type species, like the coelacanth, which is this amazing like dinosaur fish. That's studying it will tell us how bony fishes kind of evolved. This is like a very primitive bony fish. So in this solar system geology context, we're also interested in origins, this time the origins of planets instead of animals. And I'm going to make a similar prediction that instead of a sample that escaped evolutionary pressure, we might have a sample that escaped kind of geologic pressure. So in the case of geology, if we heat it up too much, if we dump it in water and then heat it up and squish it, it kind of loses its record of its formation environment. But maybe there are some samples that didn't happen to, right? Some very primitive samples. And this is where comets come in. So the best samples to look at these origins are comets. Absolutely, they're comets. So comets are cometary, and they look so cool because they contain volatile ices. I mean, some of them, like Hale-Bopp, contain carbon monoxide ice, which has to be kept very, very cold for its entire history, else it boils away and turns to gas. So these comets, because they emit gas, we know they've been kept in cold storage since their formation 4.5 billion years ago. So my primary research really is analyzing cometary material. The problem with cometary material is that it's extraordinarily hard to both collect and analyze because it's so fragile. And if it comes through the Earth's atmosphere, it burns up, it makes cool shooting stars that you might see in the night sky, and then nothing makes it to the ground. And so there's very little that I can analyze, but we do have ways to get some cometary material. We've learned a great deal from it. But the next best thing is to look at primitive asteroidal rocks. So these are more what we say lithified rocks. Cometary material has the crushing strength of soft snow. It's barely held together. Asteroidal rocks, they've seen water and heat, and so they're more like cohesive rocks. And so they're not quite as good, but luckily we have literally tons of them on the Earth's surface in the form of meteorites. And some of them are so primitive that they can tell us about the origin. So thankfully we have these meteorites and they can tell us about the origins. So if we look at these meteorites, the most primitive ones contain these very, very high temperature objects where if we understand the mineralogy of rocks condensing from a gas like the sun, but it's not hot, it's cold. So if you take the sun and cool it down and think about what types of minerals condense in that process, the answer is the first minerals are these calcium aluminum inclusions. And there are these white things that are naked eye visible in just like the Orion Nebula, but you could just see them in one of these nice primitive meteorites. So we can use that uranium lead system and date these things. And in my world, the solar system formed when the first rocks formed. So that's our time zero. This is the birth of the solar system. We use this because we can date this extremely precisely. Like we don't know when the sun ignited, but I can tell you when these rocks formed. So for me, that's the birth of the solar system, when these calcium aluminum inclusions form. So this is what we call time zero. And throughout the rest of this talk, I'm going to use these CAIs as kind of the starting point, and I'm going to call those time zero. So we're interested in the first 5 million years in this talk. And a lot happened then. And if you were sitting in the solar system and you looked around, things wouldn't look exactly as they do now. Like there's no rings around Saturn. The orbits of the gas of giant planets might be a little more compact. This is something called the NEAS model. But pretty much it's going to look quite similar to what we see today. And to just give you an idea about how fast that is, the entire solar system history is about 4.5, 4.6 billion years, right? Defined by that formation of those calcium aluminum inclusions. And the 5 million years that we're talking about today, if that entire solar system history is one day, the 5 million years is the first 90 seconds, the first minute and a half of your day after midnight. We basically got to most of the way to the solar system as we see it today. So a huge amount happened pretty much instantaneously in the solar system's history as we look back today. So in this talk, I'll just give you some overview of what was the sequence of events in the young solar system. And this is all very new stuff. And so the old view, and I said the old view, I'm talking about 15 years ago, not very long ago. So about 15 years ago, when I really started in this field, I started in more traditional astrophysics and kind of moved into this kind of cosmochemistry later. When I started, we thought that those primitive meteorites, which we call chondrites, are the building blocks of planetesimals. Those things form, they get heated, you add water to them, and then we get things like the terrestrial planets. And those planets kind of stay in their orbits, and we're pretty much done. It's kind of a quiescent system. It's this kind of linear, pretty standard progression from primitive material to more evolved things like volcanic rocks and volcanism. That happens kind of in a straight line. And it was all, straightforward, and we pretty much thought we were done, but that ends up not to be the case. So what we do is we look at these primitive meteorites, and they're super amazing. And to help me understand this, because like I said, I'm a physicist and I don't know much about rocks, and I've learned a lot the past few years. To help me do this, I developed this system to image meteorites chemically at the nanometer scale. So I construct these 100, 200 billion pixel images that are on my website and that you all can look at that show how complex and how these rocks are really cosmic sediments. So they're a collection of lots of different things that formed in lots of different formation conditions and environments. So you can see this rock, which is called ACFR 094. It's a very important primitive meteorite. It contains these somewhat rounded things, like this kind of dark thing near the middle. These are called chondrules. They're igneous objects. They're spherical. We're free floating in space, which explains their shape. And in between them is all this very fine grained material. So there's a scale bar in the lower left. You can see the wavelength of visible light is like half a micron, and we can zoom in very close to that. And we can see between these larger rocks, there's all this really fine grained material. And that is really primitive dust that's left over from that cloud that I talked about. And some of this dust contains grains that formed around other stars, these presolar grains that were mentioned by Rachel earlier. So, and this meteorite also contains these calcium aluminum inclusions, which are the green objects in this image that really were the first solids to condense in the solar system. So this is a cosmic sediment. And if we analyze kind of at the micro scale, these different objects, they can tell us about the early formation events in the solar system. So these primitive meteorites come from primitive asteroids, and it's very exciting now. We're returning actual Regulus samples from these asteroids. I think my friend Pierre Hanakour talked about this earlier this week. So I'm interested here in this talk, when do these asteroids form in comparison with planets and planet precursors that were more evolved? They separated into a core and a mantle and a crust and maybe had volcanoes on the surface. When did these very primitive things form in relation to those evolved planets? And as I said earlier, the old view was that these things formed first, and some of them accreted together and were heated to form the planets that we see today, and some of the planets that we don't see today that were destroyed. So to provide this link between those meteorites we see on the ground and the asteroids in space, the first mission to really do this was the Japanese Hayabusa mission. It returned samples from the surface of the S-type asteroid Itokawa. We analyzed them in the lab and found indeed these ordinary chondrites, these primitive meteorites that we see, do come from asteroids, S-type asteroids like this. And it was kind of suspected, and it was basically confirmation of that. So these S-type asteroids mostly consist of these round spherical objects that I showed you in that zoomable image that you can look at yourself. There's a whole bunch of them on that website. But these are really the most common extraterrestrial objects that we have on Earth. They're spherical, they're igneous. It was like this, the dust was flash melted and then cooled quickly. And so this happened in space before that that asteroid accreted to form those like asteroids like Ryugu and Bennu that we can see with telescopes today. So if you ask meteoriticists, the people that that study meteorites, how did chondrules form? You'll get about a 12-hour explanation, and nobody will agree. And they probably formed by many different processes. A more precise question is, when did they form? So we can do that. We can measure these radioisotope systems and tell you when they formed. Maybe we can't tell you exactly how they formed. So these are the kinds of measurements that I've done at various times in my career. So on the left is kind of a data plot. We look for the excess daughter isotope, and if that correlates with how much of that parent nucleus, that the parent element that we see, that gives us that ratio of aluminum 26 to 27 when that object formed in this case. So, and what we want to do is analyze not that whole rock, not the whole meteorite, but a specific part of that little spherical chondrule. And we can do that because we have these amazing instruments that are enormous. They take up basically an entire lab space. You can see the desk and the chair on the left-hand side of this image. This is the ion probe that I used in Hawaii. We have a different style of ion probe here in St. Louis. It's not quite as big, but it does the same thing. So you need these very big instruments to measure very, very small things. So this thing will measure the isotopes. It's like an ion isotope microscope. It will measure the isotope ratios at spot sizes that are microscopic. And they're really amazing, and these things have not been around for that long. So that will allow us to date these chondral objects, and it's been done in the last several years. So we can measure the dates, and that's shown there on the left. We can see a bunch of individual chondrules that were dated. And if we look at the dates compared to the formation of those calcium aluminum inclusions, we see that these things formed 2 to 3 million years after the formation of the solar system. But that's not the whole story, because what happened when this asteroid accreted is that those chondrules formed, they're free floating in space, which is why they're spherical. The asteroid accreted, it accreted with ice, and then the ice melted and creating kind of a wet asteroid here. So if we look at these formation events, we can see that asteroid accretion, that thing that we're trying to date, really lied between the time when those chondrules formed, floating in free space, and when the aqueous alteration happened on that asteroid. So we have to measure both those events, and from that we can infer when that asteroid accreted. So again, this has been done by minerals that formed, by measuring minerals that formed by the interaction of rock and water. We do have lots of meteorites that sample that type of process. And instead of aluminum 26, we're measuring the decay of manganese 53 in carbonates, so things like calcite. All these minerals exist on Earth. There's nothing super exotic about them. The exotic thing is that they contain these short-lived radioactive nuclei that have decayed since then. So this is really in the last 10 years that we're able to do this. And we found that this aqueous alteration where water's interacting with rock happened at about 5 million years. Okay, so this will allow us to constrain that asteroid accretion to be between 3 and 5 million years, right? So this is really in the last 10 years, we're able to understand this time scale of when asteroids accrete. Okay, so that's cool, and we understand that. So in the old view, the more evolved meteorites, more evolved planetesimals that separated into a core, a mantle, and a crust, and may have had volcanoes, must have formed from those objects, right? So maybe they formed after those chondrules did. That seems to be the logical thing. But recently, there's all these amazing meteorites. These are differentiated meteorites coming out of Northwest Africa, Algeria, and Morocco. And people walk through the Sahara Desert and find these incredible meteorites. This is my favorite. It's called Erdchek 002. It was found just a few years ago. It is totally beautiful because it has these gem quality pyroxene crystals, which are these beautiful green color. And they're gorgeous. They can be several inches long. So clearly, like this thing formed from a lava that cooled relatively slowly to give you these large crystals. So this is like a lava rock, but we can do the same measurement. So this is a fundamentally different type of asteroid, or really a planetary embryo, than those last meteorites I was showing you. And I have a zoomable image of this rock on my website too, and you can easily see how different it is from those primitive asteroid materials. But we can do the same measurements where we can date it, and we can see its age. And we found that Erdchek 002 has an age of like 2 million years. So really, it formed a little bit before and maybe at about the same time as those chondrules did. So this is where our old view really was thrown out, because we find that these differentiated planetary bodies formed really before or at the same time as the components of those primitive, less altered asteroids that we see today. So this is also confirmed by looking at iron meteorites. When I say meteorites, this is what most people think of. This is the Willamette iron meteorite. It's enormous, it's amazing. And we can measure a different radioactive isotope system. This is hafnium tungsten, and tungsten, like the filaments of the old filament electric light bulbs. And this tells us that this thing formed about 1 million years after CAI. So even before the Erdchek 002 that I just formed. So or just talked about. So this is really reversing this picture that we thought was true 10 or 15 years ago. And we're seeing that these planetesimals, these planet embryos form very, very quickly. And maybe these chondritic asteroids, the types of samples that we're returning from these new space missions, form somewhat later. So this is a really new idea. So far I've talked about asteroids and planetesimals, some of which probably don't exist anymore because they got smashed up to bits. The thing that most of you think about in the solar system is that you think about the planets. So the understanding the formation of these planets has been done by different methods with different levels of precision. So like when we talk about Uranus and Neptune, the ice giants, and also Kuiper Belt objects like Pluto. To me, Pluto is a planet, should be included with these things as well. We don't have samples from these, and we can't measure their isotopes. So we don't really understand how they formed or when they formed, as well as some other planets where we do have samples of. And out there, way out in the distant solar system, this accumulation that we think formed the planets closer to the sun is not very efficient. So there's different methods by which people think they form, but these are kind of theoretical ideas, and we don't know very well. So if we look a little closer, the gas giants, again, these are simulations, they're measurements of, say the Juno spacecraft can measure really the composition and structure of Jupiter pretty well. But what we think happened with them is that their solid cores, which are about 10 times the mass of the Earth, form very, very quickly. And then in the next few million years, they accreted gases that were in the solar protoplanetary disk at the time. So then they kind of grew to their current size over the next few million years. So now as we get closer to the terrestrial planets, we have samples and we can measure isotopes in some of these. So we can know exactly what they formed. And that's the precision that these kind of isotope analyses give you. So Mercury has a high density. may have lost its mantle with a collision. There's a European spacecraft called Webb Colombo that will tell us more about this in the next few years. But Mercury is a little bit mysterious in how it formed. But we have some ideas. It'd be nice if we had meteorites from Mercury. We might. I think we do. We just have to identify them. But if we had them, we can know exactly when Mercury formed. So if we go to Venus, we can actually measure isotope ratios in Venus's atmosphere from Earth. And that can constrain the time that Venus formed because we have those measurements of, say, argon, helium, neon isotope ratios. So then Earth, we have of course, we have lots of samples from Earth. So from that, we can determine when it accreted. And we know that it accreted about 60% of its mass quite quickly. So we can constrain these pretty well. But when we get to Mars, we can see in this image that Mars is awfully small. And in fact, it's a real problem. Mars is really too small. This has been kind of an outstanding problem in planetary science. Like, how do you get Mars to be so small, right? So it should have been about the size of Earth or larger. So this is another problem in planetary science. And we do have samples from Mars. We have Martian meteorites. We're going to return samples in several years that are being cached now by the rovers on Mars. But the small problem of Mars has been analyzed, or it has been, we tried to solve that problem in other ways. So basically, if we can deplete that disk of gas and dust near the orbit of Mars when it accreted, if we can get rid of that dust and gas, then that can allow us to get this small Mars that we see now. And maybe this Mars that we see didn't really go through that full process of growing into a planet. Maybe it's a planetary embryo, and then it couldn't accrete anything else after its embryo formed. And that's kind of the general idea of how Mars formed. But then we have to ask, what could have done this process of depleting that material around the orbit of Mars? What could have happened there, right? So this is kind of out of the realm of these isotope techniques that I've talked about so far in this talk. It really requires a new technique. And this is kind of a different field than I'm in, but it uses computer simulations to understand the orbits of lots and lots of objects. So we can use Newton's laws and physics if we have, like two bodies, two things interacting. And just like in physics, we can understand a hydrogen atom. But if you ask me about helium, I don't know, we got to simulate it. And it's true also with gravitationally orbiting objects. If we have two bodies, the sun and an asteroid, I can tell you what happens. But if we have thousands of bodies, now we have to grind through calculations with computer simulations. So that's what people have done. And that's another tool to understand this chronology, and really is a tool that's helped us understand the formation of Mars and why it's so small. So the general idea for this is a very dramatic set of events that happened early in the solar system's history called the Grand Tack. So this is Jupiter's Grand Tack, and it's kind of a funny word. It comes from a sailboat. Say a sailboat will tack by going one direction into the wind and changing its direction. So we think Jupiter had that. Instead of the sailboat, we have Jupiter. And we have Jupiter migrating closer and farther away from the sun. So this sounds crazy, but if you look at the physics of this, Jupiter formed, like I said, its core formed very early, and there's still lots of gas and dust in the disk. So that mass, interior and exterior to Jupiter and Saturn, pulled on their orbits. And as we depleted that gas and dust, Jupiter and Saturn's orbits changed. So this is very likely to happen, and this is one of the simulations. So Jupiter's here, the thick black line in the middle, there's Saturn. So what happened is that Jupiter drifted inward, Saturn followed it. When Saturn got close to Jupiter, it scattered all of that dust between the two orbits, and that allowed both those giant planets to move back out. So in this process, this is basically that same process. Maybe it happened in 500,000 years, something like that. Jupiter's the big circle here, Saturn, Uranus, Neptune. And there's a really important corollary to this story. So this allowed us to scatter all the stuff around Mars and allowed us to make a small Mars, which is this little circle on the bottom panel. This is an evolution. So on the y-axis is the orbital eccentricity of these bodies. And on the x-axis, the horizontal axis, is their orbital radii. So this process also scattered these dark blue things, which are like cometary nuclei, the light blue, which are icy asteroids, and the red, which are non-icy asteroids. So when they formed, they've likely formed in different places in the solar system with the icy stuff way on the outside, right? But during Jupiter's Grand Tack, we have the additional benefit that this movement of these giant planets mixed everything up, and it mixed it up and put it into the asteroid belt where we see it today. So the asteroid belt includes both of these icy and non-icy asteroids, and we ask why, and it could be because this movement of the giant planets very early in the solar system mixed everything up. So that's one important aspect of this Jupiter's Grand Tack. And again, this is a model. We don't know it happened. I think it probably happened for this reason. It explains lots of things. It didn't mean it actually had to happen, but that's the problem with these models. And that's why I like measuring isotope systems, because it's more solid evidence. So the other aspect is that during Jupiter's inward migration, it scattered these planetary embryos. So some of these things that separated into core, mantle, and crust, like we saw with that cool meteorite with those gem crystals in it. So it scattered those things to very high speeds. And these high-speed collisions between these planetary embryos and other things in the solar system would produce very unusual objects. And the important part of this is that we have these very unusual things in the meteorite record. And they're called the Carbonites, or the CB chondrites. These are probably one of the most beautiful meteorites we have. There's only a few of them. This one sold at Christie's for the price of a nice new car. I'd much rather have this meteorite than a nice new car. So it contains little blebs of iron nickel metal, and also large, mostly spherical igneous objects called chondrules. And again, we can use our same trick to date these chondrules and figure out when the chondrules in this meteorite formed. And we find out they formed very late, so at like 5 million years. So the story with this is that we need these high impact velocities to make these CB chondrites, which fall to Earth, and we have 7 or 8 of them. We have to have something exciting these speeds to make these things where it looks like a planetary core crashed into some other asteroid and made these spherical metal blebs and these spherical silicate blebs. So we need this kind of Grand Tack process of Jupiter to make these CB chondrites. And so it's a parsimonious explanation, but I believe that this thing actually happened because of all this other evidence. Okay, so then we can put Jupiter's Grand Tack there at about 5 million years, right? So now we have this totally crazy sequence of events where 10 or 15 years ago, we thought things evolved very nicely from primitive to evolve planets with core mantle structures. The planets didn't move very much. And now it's absolute chaos. Things were crazy. We're forming these lava worlds very, very soon. We're forming differentiated planets very soon. We're accreting these primitive asteroids very late. Jupiter's moving in and out. Neptune and Uranus were following. So it's total chaos now. And I think it's super exciting because this is, there's lots to do and lots to understand. And these exoplanetary systems that we're seeing elsewhere probably went through similar chaos, right? We're seeing them at a snapshot in time. We're seeing like hot Jupiters that are very close to the sun. Well, maybe we had a hot Jupiter when Jupiter tacked in close to the sun. So maybe it's not so weird. Maybe these are systems like our own. So just in the last couple minutes here, that was the past. So I want to just briefly talk about what we might see in the future. I talked about these colliding planetesimals that produce these crazy CB chondrites that we're seeing with the metal and the silicate spheres in them. Can something like this happen to us in the future? So basically, Hollywood says it does. And they've made several movies about this of varying quality. Depends on your taste in movies and stuff. But there's one just recently called Don't Look Up about a cometary impact. So that's not important. So what does the data say here? And this is a plot. It's called a log-log plot. And scientists use this to put very different scales on the same plot. So we can see that things change. This is an exponential notation, but things that change by a factor of 10 for each tick on the y-axis, and change for a factor of 10 on the x-axis as well. And what's being plotted here is basically the number of impacts of a given size, diameter, or energy and the probability of that happening. So we have it's highly probable we have a lot of very small impacts, and then we have fewer larger impacts. But the problem is that we don't have very good statistics for this, and it's quite unknown. So, and the largest things don't happen very much, so we can't really tell if this is just random luck or bad luck, or how frequently these things actually happen. So there's a couple important recent events on here. This very mysterious Tunguska event, which happened in Siberia in about 1908, was an enormous explosion. It was tens of megatons of energy. It was incredibly energetic. It knocked over trees. Maybe a couple reindeer farmers saw it. That happened in a very remote area, so there weren't many eyewitnesses. No materials found, which really has confused me, but it's an enormously powerful event. And it has happened more, it was only 100 years ago. It was only one time, but it should be very unlikely from our understanding of the impacts of these events given observations of near-Earth asteroids, right? So that, is weird. And you can say like, oh, that was just a random bad luck thing. But then about 9 years ago, there's a very huge meteorite fall in Chelyabinsk, Russia, which also was very, very energetic. It was so powerful that it knocked over a couple buildings. Maybe those buildings were in great shape anyway, but it did knock over a couple buildings. People got hurt from broken glass. So they saw this giant fireball in the sky and ran to the windows to see what happened. And then the shock wave came and broke the glass. So a couple of people got hurt. Nobody got killed, but it was kind of a warning sign. And also to me was evidence that maybe some of these very large events aren't quite as rare as we thought. So then another thing happened like 4 years ago. This is the Kamchatka superbolide. Again, it was in Russia. It was very, very energetic. This is a satellite image. So we saw this smoke trail from space. No meteorites were recovered. It's a very inhospitable area with lots of grizzly bears. But again, it was something very, very energetic, which should be very, very unlikely. So we're seeing some of these energetic things that shouldn't have happened. And the other problem is when you have a meteoroid coming through the atmosphere, this damage that it does is directed along its flight path. So it's directed at the ground. And if we compare its like explosive power to say like a nuclear bomb, it's worse for these asteroids because it's directed to the ground. Okay, so these are some like newly discovered, like these simulations were just done a few years ago. So maybe these things are causing more trouble than they should, given their energy. So what does the data say? So this is the data we have, and what we're trying to do is extrapolate it out to the really big things, right? So the 10-kilometer object is like the asteroid that killed the dinosaurs, that wiped out a lot of life on this planet. We don't want that to happen. 1 kilometer is really, really bad. We don't want that to happen either. And so we can extrapolate this data. And if we look at just telescopic observations of near-Earth asteroids, small objects, we could see that this isn't really a problem, right? Like the 1 kilometer happens every 10 million years, 10 kilometers every 5 billion years. So we got nothing to worry about, right? But this doesn't seem right because the dinosaur event happened 65 million years ago. But now if we look at we draw this extrapolated line from that Tunguska event and that Russian meteorite from 9 years ago, and even that Kamchatka event from just a couple of years ago, it gets a lot worse. So these really bad events happen every 1,000, 2,000 years, and the dinosaur killers seem to happen, more frequently. So the answer is when people ask me this, I don't really know, right? So, and there's a lot of uncertainty here, and that's the problem with small numbers. We only have single events, and extrapolating this out to the larger objects, right? And the other problem is this little curve in the near-Earth asteroid data, which are these green squares. You can see this kind of curves up. So if we extrapolate it that way, then we got a different answer, right? So we don't really know. And to me, to be a responsible species, we should be looking for these things. And this is Planetary Defense. And there's some telescopes that we're kind of using to look for asteroids that might hit Earth. The problem is these are small and dark objects that are moving close to the sun, so they're very hard to see. And are repurposing telescopes used for other purposes for this. So it'd be nice if we had a dedicated telescope to look for these things, and hopefully that's coming soon. And the other aspect of this is if we do see something and we have enough warning, what are we going to do about it? And this is really the goal of this DART mission. which is NASA's first planetary defense mission. It was launched in November. And what it's going to do is impact Dimorphos, which is kind of a moon of a larger asteroid. It's just going to slam into it. It's going to drop a little satellite before it does that. And what we're going to do is watch how that kinetic impact changes that orbit of that asteroid. In case in the future, if we have something coming close to Earth, how far and how large of an object do we need to hit it with to deflect the asteroid enough so it just misses Earth? So this is exciting. I think we're being a responsible species and that we're thinking about these things, and it's something to look for in November. Okay, so that's what I have today, and I can take any questions now. Thank you.
Let's give him a great big round of applause, everybody. Thanks so much, Ryan. Just mind-bending kinds of stuff. Or maybe it only bends my mind, not yours. And definitely and not Rachel's, but certainly thinking about, you know, what was going on billions of years ago. And then the fact that there are signatures of these things, there are remnants of them, and you just have to look close enough and you can just write the whole story or most of the story. I'll remind everybody watching, drop your questions over in the chat because we're going to turn to those in the last few minutes that we have here. And we had some really interesting questions come in, really great ones. And Rachel was doing a great job of answering some of them or building discussion on some of them in the chat here on Zoom. But I want to break them out for our YouTube viewers as well. David had a great question, and I just got to find it. How do you know the planetary origin of a meteorite?
Right, so we don't really. There's been only 2 meteorites that we saw. We detected them before they hit Earth. And they're both really, really weird meteorites, which always doesn't sit well with me. And some of them, we can look at the fireball and reconstruct the trajectory later. And we have probably 30 or 40 of those. But that meteorite orbit doesn't really tell where it formed because these small objects have interactions with the planets and other things that really change their orbit from where they started. That's not true for everything. Some of them kind of preserve their primordial orbit. Jupiter protects some of these asteroid families, but it's a very hard problem and it's unclear to me. So I think that's really an open area of research.
Okay, and Rachel was talking a little bit about like comparing spectra or I guess isotopes of the meteorites with what we know about the compositions of the planets, or in the case of the moon, how we can just look at the pieces of the moon that we brought back.
Right.
So we can't do that with anywhere else.
Talking about orbital, right. So we can look at its composition, its mineralogy, its geology, some isotope systems. And that's what led us to determine that the SNC meteorites, which is a very specific class of meteorites, they had some trapped gases in them. And we analyzed those gases in the meteorites, and we found that those matched the gases that the Viking lander on Mars measured. And so that allowed us to link the SNC meteorites to Mars. The lunar meteorites, we have a few of them. Nobody's ever seen a lunar meteorite fall, but they found them later. And if somebody had one of these in a conference, maybe Rachel remembers, but it was a meter size, it seemed like a meter sized piece of a lunar meteorite that just looked like the moon. I mean, I could ask my son where that meteorite came from. He's like, oh, obviously it came from the moon. And its detailed mineralogy and isotopes would match, some of the Apollo samples, but it was pretty clear to me just by looking at it that it came from the moon. Yeah, it was really cool. It was like a $300,000 meteorite.
Oh, wow. Goodness. All right. Next one is from Leah. Is there any kind of systematic elemental asymmetry in accretion disks that would cause roughly monotonic variation in core planet composition versus distance from the sun?
Yeah, that's a great question. So,
and I was able to read it. Yeah. So I'm very proud of myself.
So, I don't think so. That's a really interesting problem. So, people have speculated, like, there might be, say if we look at hydrogen isotopes, just as a simple example, they basically have two stable isotopes of hydrogen, deuterium and hydrogen. And some of the comets look like they have more deuterium than hydrogen, and some of the water spectra from terrestrial planets looks lower. So maybe that means there's like a monotonic increase in D to H, and that's kind of what I thought was the case when I came into this field as a physicist. But I think in the last 15 years, I've understood that these chemical processes and the solar system was so mixed up that I don't really believe that that's the case anymore. In general, we have ices in the outer solar system, and those wouldn't exist closer in where it's warmer, and those ices would sublime. But the details of that are so intricate that I don't think it's a useful model. I think planetary formation and planetary evolution is incredibly complicated, and chemistry is complicated, and it's more important to look at like planetary processes and kind of these global scale chemical things. Rachel probably disagrees, actually, but what do you think?
I may have misunderstood her question because I was trying to comment in Zoom. Is that I was just thinking of the snow line, really. And if I didn't understand the question, apologies, Leah. But it was more about, I thought she was asking about where generally these planets form, if we have a model for that. And so I was answering it by way of just talking about the snow line, and you have certain elements that will condense outside the snow line and certain ones. So we have terrestrial planets generally within the snow line and gas and ice giants outside the snow line. That said, you talked about some models which get more complicated, right? Because nothing's perfect. So we observe our solar system, and yet the models don't exactly fit. And so we have what Ryan mentioned was the Nice model, and there's a Grand Tack scenario. And those are complicated models that are hard to, I don't even barely teach about them because it's not you really need a specialized, kind of class in that, is that then the planets migrate and they move, and you need a model. It's hard to really understand. I think, Ryan, you conveyed this really well. It's really hard to understand early evolution. We can't look back in time beyond these little bits of material. And so the predictive value of them is hard to determine, right? So we observe our solar system, we have limited data on exoplanets, and we don't know in great detail how we barely observe maybe a moon in an exoplanetary system, and that's probably debatable. So we don't have all the data. And so it's hard to know, I think, how well these models fit. Brian, you can correct me if I'm wrong, but I feel like you said, the arguments, you ask a cosmochemist and you'll get 5 different variations of an answer from each person, and then they all yell at each other about it. So
it's job security.
That's kind of what happened. Yeah, job security. But it's a really good question. It's a really good question to ask, because it just gets into this idea of how do we even ever find these answers, right? Like the origin of life. I mean, we can't go back and sample these. We have limited observations. Mm-hmm. And so if we're talking about planet formation, we have planets. We're on a planet. We can go to another planet and all that stuff, and generally understand what happens on a foreign planet. We could try to do better than what happened 4.5 billion years ago. So it's very hard, and we are trying to do it. But these are great questions. So I hope I'm not sure if I helped.
Oh, definitely.
This was really interesting, Ryan. I just want to say this was a great talk.
Oh, thank you.
Everyone enjoyed it. And
absolutely agree. Great presentation. Thanks for being with us today, Ryan.
Yeah, thank you for having me.
Thank you so much. And next time in person, all of our speakers hopefully will come back next year when we convene, hopefully in person.
Awesome.
Absolutely. Well, folks, we're going to get off here. That way you can all get to the next presentation that starts in, about 20 seconds. So make sure that you check out naturalsciences.org for all of the museums, programs, and events that are coming up for the remainder of today and on into the future. And we hope that you have a great rest of your Sunday. Bye, everybody.
Bye.
Thank you. Bye.